Now we have another microscope. A compound microscope has an objective with a focal length of 3 millimeters and an eyepiece with a focal length of 6 centimeters. It's adjusted for minimal eye strain with a near point of 25. If the two lenses are separated by 40 centimeters, what is the overall magnification? Let's draw it out. We have got our objective and our eyepiece. FO, FO, our eyepiece is FE. We have that the focal length of the objective is 0.3 centimeters. Look at that. And we have that the focal length of the eyepiece is equal to 6 centimeters. We know that the distance between these two lenses is 40. All the units I'm keeping in centimeters if I don't clarify that. So we know that the distance between these two lenses is 40. But that is not our length. Remember that our length is between the objective lens and the focal point of the eyepiece. We can find that actually pretty easily. We know that the distance between the two is 40, and this one is 6. So we can say that L is equal to 40 minus 6. Equals 40 centimeters minus 6 centimeters. We get L to be 34. The magnification equation is MOME which is equal to negative L times 25 over FO FE. Where this 25 is coming from is it's built into the equation that our observer has a near point of 25 centimeters. We've built that into all of these equations. That's just assumed. So if it says it here, then that's kind of just redundant. But when you see this 25 centimeters, that's referring to a person's near point. We can plug this in. We get minus 34 centimeters times 25 over 0.3 times 6, giving us a total magnification of minus 472. This should probably be minus. That is the second one with a microscope. Now let's get to telescopes. The objective lens and the eyepiece of a telescope are 0.9 meters apart. The telescope has an angular magnification of 40. Find the focal length of the eyepiece. Let's draw it. Telescopes are different from microscopes. We have our objective and our eyepiece. In this case, you'll note the objective is actually bigger. So our focal length is actually going to be really far out, to the extent where I'm actually not going to draw it on this side. There's one on both sides, but I'm just not going to draw it so we have room to actually do the math. It's going to have its focal point is going to be like, let's say here. It would actually be like farther out. The eyepiece is going to have its focal point at the same spot. So the objective and the eyepiece should both have a focal point at the same spot. We've been told that the distance between those two is 0.9 meters. Our magnification is 40. Actually, it should be minus 40 because it's inverted. And our equation for magnification is minus f objective over f eyepiece. We do not have either of these though, so we're going to have to get a little bit creative. What we do have is we do have m, and we can have some fun from there. We know that FO plus FE is going to equal 0.9. We can rearrange this to get it in terms of FE. So you can state that FO equals 0.9 minus FE. We can plug this in up here. We can say that M is equal to negative 0.9 minus FE over FE. This comes out to, we have the minus 40, so we're going to plug that in for M, because telescopes create an inverted image. So we have the minus 40. That is going to equal minus 0.9 over FE plus, distribute that negative, we'll get an FE over FE, which is equal to 1. This is equal to negative 0.9 over FE plus FE over FE. Do some algebra, so switch the signs and we get 40 equals 0.9 over FE minus 1. 41 equals 0.9 over FE. And from there you can just find that FE equals 0.022 meters. Now, to find the focal length of the objective, we can actually just use this one right up here. FO equals 0.9 minus FE equals 0.9 minus 0.022, giving us FO is 0.878 meters. There's some examples. Hope that helped.